Now, what we can do is to take, using this relation, to take this expression of B and E in terms of the potential and to substitute them in the Maxwell equations. And after some algebraic manipulation, we can write some equations which are totally equivalent to the Maxwell equations, but involving not the electric and the magnetic field, but the scalar potential and the vector potentials. And so we obtain these two equations. This is for the vector potential, and this is for the scalar potential. Here I have also introduced the speed of light c in terms of epsilon and mu. Now you see that this equation for phi is exactly the Poisson equation for electrostatics. And this is very similar to a wave equation for the vector potential. However, you can also see that these two equations are still coupled equations, because in this equation appear both A and phi. So we need some trick to obtain two equations, one only for the vector potential A and one only for the scalar potential phi. Okay, this I will not go in much details on this because it's not an essential point. Can be done in this way. It exists a theorem due to Helmholtz that states that any vector field, and in this case the field is the current density, can be separated in only one way, in one field which is called the transverse, and is such that its divergence is 0, and a field which is called the longitudinal, such that its rotation is 0. Now, what we can do is to take this equation and separate the transverse part and longitudinal part of this equation. The essential point in all this is if we do that, at the end we obtain an equation for the vector potential that does not contain the scalar potential, but it's only in terms of the vector potential. The only difference is that as a source term for this equation is not present the total current density, but only a part of it, that it's transverse part. Now, you see that if we do in this way, we get an equation for only the vector potential, which is a wave equation for the vector potential. Now, if we assume to be in vacuum space, in the sense that we assume that there are not electric charge or currents, we can put J equals 0 and also rho equals 0. And so, if J equals 0, R0 also is transverse and longitudinal part, and then in this equation for the vector potential, the right hand side is 0, and so we obtain only at the end, in the vacuum space, this equation for the vector potential, which is a wave equation. Until now, all what we have done is still classical electrodynamics. And now we assume that the field we are considering is, for example, inside a cavity. Now, if we want to solve this wave equation for the vector potential in the cavity, first we know that in this equation, which involves space derivatives and also time derivatives, we can separate the variables. So we can write the solution as a product of a space function and temporal function. So what we can do is to make a Fourier expansion of the vector potential in terms of the modes of the cavity. And this is the expression that is obtained for the vector potential. Now, the modes of the cavity are given by the wave vector, and here we have a summation over all possible wave vectors which are compatible with the boundary conditions given by the cavity. And you see here we have the space function, which in this case are complex exponentials, and also some functions of time, and there is one of these functions for each mode of the cavity. And the general expression of the vector potential is a summation of functions of this kind over all possible value of k, and also you can see there is a sum over j, which is a polarization index for the field. Because this field is a vector field, so it can have for each mode in principle 3 different directions in space. But what is possible to see from the fact that we are using the Coulomb gauge is that the direction of the field given by the polarization vector must be orthogonal to k. So we have this situation. If this is the direction of the wave vector, the polarization vector must be in a plane that is orthogonal to k. So there are only 2 independent polarization directions. This is the reason why this sum over j has only 2 values. So 2 independent directions in a plane orthogonal to the wave vector k. And this is the so-called polarization unit vector that gives the direction of that particular mode of the field. Now, if we use this expansion, this Fourier expansion for the vector potential, and we substitute it in the wave equation that we want to solve, what we can find is an equation for these amplitudes. In the sense that here you see that the space part of the function is explicitly written, but these amplitudes are still we have not yet determined them. So we need some equation for the temporal behavior of this quantity that we can obtain using the wave equation for the vector potential. And if we do this,